So either of you guys or you guys, do you have any questions in terms of 4.4? Yes, no, not sure, have a clue, where are we at? Have we looked at the problems? I guess that's what I'm getting at. And so in looking at the problems, is it just like, I'm not really sure? Or, yeah, I've got this, just trying to get a feel for where we're at.
There's a couple where I'll start off not really knowing what I'm doing, but looking at examples and helping me solve this.
Okay,
Typically.
kind of get through it.
Yeah.
Okay. So I think what I'll do then is just kind of jump back to the beginning. And you've looked at it a little bit, so some of it will kind of come together. But we are looking at numeration system. We use a positional place value system. It is uses what we call base 10. Now, what that simply means is I've got 4,567. So behind the scenes, what this really is 4 times 10 to the third plus 5 10 to the second plus 6 times the first. Don't really have to write one there, but putting it there so we can see the powers descending. And that's why we call it thousands place, hundreds place, tens place, ones place, anything with 0 power is 1. And why we say we use a base 10. So we have what we call base values, those are the digits, and then we got place value, where each digit is placed that it is occupying. Now, the deal is the base actually doesn't matter. You can work with any base, and that's what this section is really about, is looking at other bases. So if, for example, now incidentally, if I didn't say it, this is called expanded form, writing it up. Okay, so if I have a number like this, 7, 6, 5, 4. I'm going to put this number in base 8. We're going to work with another base. Now, so a couple things. If you're working in another base, as far as verbalizing this, don't say 7,654. You're just going to say 7654 base 8. Now, the reason is that verbalization, when I say 4,567, those words are connected to base 10, 7,000. So we won't have that with base 8. All right, and we write if we're working, this number is actually in another base. You write it out in letters. You don't just use the numeral 8. You don't want to confuse it with an actual digit. You always put it in the subscript. On my math lab on the homework, if you've gotten in there, you would have noticed when you input answers, it always actually gives you this. You don't have to type the subscript in. Now, so the first thing what we're wanting to do is be able to convert from base whatever back to base 10. Get its base 10 equivalent. And we're going to look at a couple ways to do that. Now, write it out in expanded form. And this is where you see it's base 8. So you don't get 10 to the third, you know what? 8 to the third. And 6 times 8 squared plus 6 times 8 to the first plus 4 and 5. 4 times 8 to the 0. So from there, you get its base 10 equivalent, you just do the arithmetic. And so, So if you happen to have an 84, you can type this out in one string. If you're using a scientific calculator like on your phone, you're gonna actually have to find 8 to the 3rd, multiply it by 7, and then you find that product, and then add that all up. So for this one, and on the calculator, like on an 84, you don't even have to worry about the parentheses. It'll sort out the order of operations. Plus 6 times 8 squared plus 6. Five times 8. And I would just go plus 4. You can put plus 8 to the 0, but 8 to the 0 is 1, so you're just multiplying by 1. Right, so I get 4,012. The only one base that we don't write is base 10. So when you don't see anything written here, you know it's base 10. Good. All right, so that is one way to convert from any base back to base 10. Just write an expanded form and do the arithmetic. Now, there is what is called the calculator shortcut. And there were problems in there. In fact, one of them is it's an attention to detail problem because it works with base 2 in doing that. So if you have a calculator, get a calculator real quick. I'm going to do this on my calculator. Oh, no. You got to probably have one at a time. And this shortcut I'm going to show you is meant for a calculator like it's on your phone. That it works binary. You can't, like a grade 4, you can type everything in like that and just hit enter. One on your phone's got an equal button. So, calculator shortcut. What I'm going to do, I'm going to convert this. We already know we're supposed to get 4,112. Start here, and there's going to be a pattern to this. You're going to go take the first digit, 7, times the base. Every time, now if you're on an 84, hit enter. If you're on your regular calculator, hit equal. So 7 times 8, 56. Right? Add the next digit. So plus 6, hit equal. Times the base. Hit equal. Plus the next digit, which is a 5. Times the base, which is 8. And then plus the last digit, which is 4, one's place, you should see 4,012. Get it? Now that's called the calculator shortcut. So it's, and if I'm doing quick calculations, that's what I do. Or it's actually quicker than trying to punch all this in with 984. So the way it always works, the first digit here on the left times the base, plus the next digit, times the base, plus the next digit, times the base, plus the ones. Calculator shortcut. Now, why does that work? So what I'm going to do is I'm going to take that expanded form. 7 times 8 to the 3rd, plus 6 times 8 squared, plus 5 times 8 to the 1st, plus 4. And what I'm going to do is just rewrite this. Now, again, what I'm up to is I want to see why this works. And I'm just going to factor out factors of 8. Now, there are 0 factors of 8 here. So I can't factor out an 8 out of there. There's no actual factors of 8 there. But those 3 I can factor out at least one factor of 8. So I factor out the 8. I'm going to put in a bracket here just to keep things organized. So what I would have here is 7 times 8 squared plus 6 times 8 Now here, I factor out the loan factor of 8, so I'm just gonna write +5. And here, outside of there, I'd never factored that out, so I got the brackets here. Good so far? So all I've done is factored out 8 out of those 3. Then I'm gonna do it again. I can factor out one factor in here. Now that's gonna leave me with 7 times 8 plus now just 6. Then plus the 5 plus the 4. That's as much as I can do. Now this is called nested form. Now, order of operation says work what? Innermost, right? 7 times 8 plus 6 times 8 plus 5 times 8 plus what? 4. So it's just a simple, the reason the calculator shortcut works is a simple result factor. Now, when there's going to be some homework problems, and there's about 3 of them. And they say, write it out using the calculator shortcut. And I've been on one of those, there's been things through the years, and it's not just because I write them and they change it. It's for platforms used all over the world. But enough people say it now, they'll eventually change. You're not going to write it like this. If you do, it'll count it wrong just syntactically. What they do in the problem set is actually write it right to left. How you do it, though it's going to be equivalent, but when you write it out that way, you can't actually see why it works. But I'm just giving you a heads up, and they use all parentheses. Now, so if I were to, so this is, this will save you some frustration in terms of writing it out. So the first thing we would do is go what 7 times what 8, and then plus the 6, right? So 7 times 8, and then plus what 6, right? All right. Then we'll throw parentheses there. Because then after that, you're going to multiply by what, 8 again? So they write it on the left there. Then we add the next digit, right? Which was what 6. No, I guess that's 7 times 8 plus, yeah, plus that. So the next digit is what? 5. Okay. Then all this gets multiplied by what? By 8 again. All right. Then we add the next digit, which is what? 4. And so 7 times 8 plus 6, then that times what? 8 plus the 5, then times the 8, then plus the 4. All right, so you may want to copy that down just for reference, because that's how they're going to want it. Now, also, don't use, I like to use the X. They also have the dot. But if you use the X, do not use the letter X on the keyboard. It will count it wrong. And it won't tell you why, it'll just say wrong. Use the X on the toolbar. But you can also use the dot, but also on the toolbar. You good? Okay. Guess my warranty's expired. All right. So another important fact about working in other bases with our enumeration system. Whatever the base is for our positional place value system to work, you have to have that many digits exactly. So think about it, base 10. How many digits do we actually have if you count them up individually? How many digits do we use? Do we know? What are our digits? That's it. 0, 1, 2, 3, 4, up to what? And how many digits is that? 10, right? So whatever your base is, you have to have exactly that number of digits. So like on base 8, what are the digits of base 8? That's exactly it. That's it. Right? If I would write out, wanted to keep going, if I were going to keep writing out numbers consecutive in base 8. So I'm not going to put the EIGHT here. One group of 8, no ones. One group of 8, 1 1. One group of 8, 2 1s. Looks just like what we're used to. Now think about it. One group of 8, no ones. It's 1 times 8. That's 8. 8 plus 1 is what? 9. 8 plus 2 is what? 10. These are the base 10 equivalents. Okay. So base 2, if you were working in base 2, what would be your digits? 0 and 1. That's it. Which is really important for us because that's what computer coding is done with. Chosen back in the 30s when they first started programming to use base 2, and the reason was they could use the 0 and the 1 as switches on off. And if you think about a power switch on a computer, or there's other items. I know at one point or another, all of you have seen a power switch, and off had a 0 and on had a 1. Okay, so and we will look at what is called ASCII, which stands for, its acronym, American Standard Code of Information Interchange. Every letter of the alphabet, uppercase letter, and every lowercase letter is assigned a 7-digit binary number, which all of them, you can get the base 10 equivalent. So I'll throw this out there. Any nerd, you guys are nerds like me, familiar with series of books, and the first book of the series was called Hitchhiker's Guide to the Galaxy. All right, they made a movie. You guys know the movie, but probably 10 years ago. All right, good enough. Fair enough. All right, so there is a book. It was wildly popular, and it's actually been in the news. Kind of why I brought it up. It was last week or the week before last. The author of said book, Hitchhiker's Guide to the Galaxy, a guy named Douglas Adams. He's passed away now, but it was the 42nd anniversary of the release of the book. Now, if you're familiar with Hitchhiker's Guide to the Galaxy, you immediately know what 42 means, or why it's important to the book. Any idea? All right, so it's a kind of a science fiction kind of comedy book. But they build in the book, they build a supercomputer, ginormous computer, and its sole purpose was to find the answer of life, the universe, and everything. That was its goal. And for a millennia, it worked on this problem. When the final, the day of the answer comes out, and it answers one simple answer. It says 42. That's the answer. Well, anyway, so this is kind of silly. Well, kind of good. I know where Douglas Adams came up with that number. In ASCII, then every single letter is assigned, like the uppercase letters A through Z are 65 through 90, 27 letters, one correspondence. And the lowercase letters are assigned 90 through 122 or something like that. Anyway, also all punctuation is assigned a number. So every kind of period, comma, any kind of punctuation you can think of. And if you are in computer coding and you're writing out code, an asterisk is what is called a wildcard. And the asterisk in ASCII was assigned number 42. And if you're a computer coder and you use an asterisk, its translation is whatever you want it to be. So what is the answer to life, universe, and everything? Whatever you want it to be. Anyway. So if we ever really get back to trivia nights again, more useless trivia for you for a trivia night. All right. So another, now, base 2 has practical application. Base 8 has practical application, but there's also another one that has practical application. Because we can work in any base. One that we will work with because is base 16. All right. So what's the first problem you can think of working in base 16? How many digits would you have to have? How many digits do you have to have for base 8? How many digits do you have to have for base 2? How many digits do you have to have for base 10? And how many digits do you have to have for base 16? 16 digits. We only know what? 10. That's all we got. We have 10 digits we work with. So, and this is standard. Base 16, by convention, those other digits beyond the 10 we know are assigned capital letters. A, B, C. Yeah. Now, every time I work with base 16, I've been doing this forever. I write down. When I do my calculations. Those are the numbers you can't plug B into a calculator. You can on 84 if you store 11 into B, capital B, but anyway. So if I had a number in base 16, like BC3, base 16, and I said, convert that to base 10, then this would be B, base is 16, so in this case, 16 squared, plus C times 16 to the first, and plus 3 times 16 to the 0. Then when I do the actual calculation, so whether I use the shortcut or just put this in on my calculator, guys, just so right there. Then when I do the calculation, I'm not going to put B and I'm going to put what? 11. And I'm going to go 11 times 16 squared plus, and then C is what? 12 times 16, and then plus the ones place, which is 3. And I come up with 3,011. And you always expect, you know, if the larger the base, the less digits you need to represent a number. You know, move to a smaller base here, so I was going to need more digits. That's fairly standard. All right, good so far. All right. So what if I want to convert from another, or from base 10 to another base? That is going to the other direction. So normally I would actually show this 2 ways and say 1 way's, you know, kind of see how things work, why it works, but there's a more efficient way. And just because of time's sake, I'm just going to go to the more efficient way. I'm going to start with this one. We already know the answer. We know that 7654 base 8 is 4012. So I'm gonna say, what if I had given you 4012 in base 10? And say convert. Base 8. What would be the algorithm? What's the process? Right, so this requires division. Finding quotient and remainder. Whatever the base is you want to convert to, you're going to divide into that number in base 10 by that base. So 8 divided into 4012. All right, so on your calculator, you're going to go 4, 0, 1, 2. Divide by 8. Now, you actually get 501.5. So that means the quotient, which I'm going to write right here, that's how many times it divides into, is 501. The remainder is not 0.5. And it's not a half. The remainder, that decimal part, whenever you divide on any calculator, is the decimal form of a fraction, remainder over divisor. I'm dividing by 8. So if it's 0.5, it has to be a form of 1/2, right? And so with the denominator of 8, that'd be 4/8. So that tells me the remainder is what? 4. Now, that's, you can do it that way. Sometimes though you divide and you get like a whole string of numbers in decimal form, and it's like impossible to know what fraction that is exactly. Particularly if you're working like going to base 16. So process, this will work every time. Finding the remainder, divide into this, the number, the part of the number to the left of the decimal point, your quotient. To the right, figure out what the remainder is. Just go 8 times this. 8 times 501. And you get 4008. Subtract that from this. That's why you got a remainder of 4. And that'll work every single time. All right. Now, we're going to continue this process. And it will end the same way every single time. We're going to keep dividing by 8 until I can no longer divide by 8. And we're going to end up with a 0 quotient at the end. Every time, no matter what base you convert it to. So we'll see it here in a second. So I'm going to continue on. 501 divided by 8. Goes 62 times. All right, now the remainder, if I go 62 times 8, I get 496. So that tells me I've got to have a remainder of what? 5. And you do get to a point you really don't need the calculator anymore, hopefully. 8 divides into 62. How many times? 7. Now, 7 times 8 is what? 6. So my remainder is what? 6. All right. So here's the right at this part right here. So this gets sometimes a little squirrely when students are first learning it. You're going to get to a point that the number here is smaller than what you're dividing by. 8 divides into 7, what? 0 times. That's where the 0 comes from. And the remainder is that number right there. Every time, without exception of fail. Now, how do I read? We already knew what the answer was. So how do I read this? Bottom up. 7654 basic. That will work every single time. All right. So from there, let's do another one like that. Let's take 4,532. Let's convert to base 16. All right, so that means I'm going to be dividing 16 into 4,532. Here we go. 4, 5, 3, 2, divided by 16. Now I get 283.25. Okay, so remember that I'm working base 16. Have that handy. So 283 times 16 is 4,528. So my remainder has to be 4. And then I'll continue on. 283 divided by 16 goes 17 times. 17 times 16 is 272. So 272 taken away from 283 is what? And I wanted to. So what is 283 minus 272? 11, right? It's 11. So my digit would be what? Then 16 will go into 17 one time with the remainder of what? 1. And then 16 goes into 0 one time. All right. So it would be 1, 1, 8. Good. All right. Now the one base that I'm just doesn't matter which direction I'm converting, whether I'm going from base 2 to base 10 or from base 10 to base 2. I tend not to use these methods because of the fact of what base 2 is. Base 2 has 2 digits, either 1 or what? 0. Anything times 1 is itself, and anything times 0 is 0. So for base 2, if I have a base 2 number, 1, 1, 0, 1, 1, 1, 0, 1. All right. Let's make it base 2. What I really do here, if I'm working just base 2, I just think about powers of 2. That is, and I would have handy, so I wouldn't have them if I didn't know them by heart. But literally 2, 0, 1, 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th is 64, 2 to the 7th, 128. And we'll go one more, 256. So what I do if I'm working, like say I want to go base 2, I want to do a quick base 2. I could write it out in expanded form. I could use the calculator shortcut. They would all work. But really, I would think this is 2 to the 0 place, that's 2 to the first, 2 square, 2 cube place, 2 to the 4, 2 to the 5th, 2 to the what? 6. Anywhere I have a 1, I've got that power of 2. Where I have a 0, I don't have that power of 2. So 0, 1, 2, 3, 4, 5, 6. 2 to the 6 was what? 64. And plus 32. But I would not have the 16, but I would have the what? 8. 4, and the what? The 2. Everyone see why? Just those. And then I would add them up. What? 110. And you probably could do this magic trick that I failed miserably once upon a time. Went to a conference years ago, many years ago. Anyway, I was just looking at, there were all kinds of different sessions you could go to, and I saw this one mathematics. All right, go check it out. Guy was brilliant. Really cool tricks. He had laid out 10, I think there were 10 of them. There's little coin kind of things you can squeeze like that and that change them. You know what I'm talking about? And I don't really see them that much anymore. They used to be popular like a long time ago. Kind of like these things you can put change in, push them like this, and that's going to change that. He had 10 of them lined up there. And he said, give me any dollar amount between 1 cent and $5. All right, $3.82. And he said, pick this one, this one, this one, this one. Dump out the change. Don't mix it though. Just keep piles separated, but add up, all the piles and add up all the money. So you do that, and then it would come up to $3 and whatever I said, 82 cents. Every time. Never failed. Well, the thing was, I was very impressed. I did catch on real quick to what he was doing when he said, don't mix the piles. And then I actually could see what the dollar amount was. First coin, has a penny in it. Second one had what? 2 pennies. Third one had 4 pennies. Next one after that had a nickel and 3 pennies. Next one had 16 cents, then 32 cents, and then what? They were all exactly powers of 2, except the last one to make the trick kind of sound good. It had 88 cents, which is not a power of 2. That was just rounded off to a number. In his head, this was what made it impressive. And I remember asking him, how did you do that? He was able to add those power of 2s like that. I mean, you just tell them $3.82, and he can figure out the powers of 2 that you would need to add up to be that number like that. Anyway, that's not easy to do. I asked him how he did it. He said lots and lots of practice. I believe it. I tried it, and it failed. It was an epic fail because I wasn't able to quickly on the spot add up these powers of 2. But any counting number, any natural number can be found by adding up a unique combination. So there's only one combination worth of powers of 2. All right, so all right, another number 2. All right, so guys, I can't show you this out there. It is on page 173 in the e-text. I'm looking at this table 14. This actually back in the 70s, and I remember seeing it. I don't remember what the cereal was. Something with a lot of sugar in it, I'm sure. Was a game on the back of the cereal box called Age Detective. So you've got these columns that you can barely, it's kind of cut off the top A, B, C, D, E. Okay.
Who, now, don't tell me, I always throw this question out, somebody, will get somebody just works their age out. Don't do that, but who is not afraid to say how old they are? Like, everybody's afraid or not? Not afraid?
No.
All right, we'll start with you.
Did I actually tell you now?
No, don't tell me.
Oh,
I'm gonna tell you. I'm gonna tell you how old you are.
okay,
But what I need you to do is look at that table, table 14,
okay.
and tell me what columns, every column, your age appears in. Five left.
I think it's. I don't remember this, I just want to make sure.
It's okay. It's all right. We'll know here in a second if you do this one.
A, C, and E.
A, C, and E, you're 21. A, C, and E, right?
Yeah,
Are you 21?
yeah.
Okay. Then you found one. Okay.
A, B, E.
A, B, E, A, B, E, you're 19.
B.
B and E, you're 18. Where you at?
A, B, E.
A, B, E? A, B, E, you're 19 then as well. All right. Incidentally, this table is way too small for me. When I first started working here, we could use this table to figure out. When I started working here, I was 26. So, yeah. So how am I doing it? I'm obviously not looking at what the columns, trying to find some sort of intersection. Did anyone pick up on how it's going so quick?
I just popped up
It's a
one of the
question.
questions and
Yeah.
it tells me what you did.
Okay. It is a problem on homework. Look at the top row. Those are all powers of what? 2. And so the way the table was built, if I were building it, I would put my 1 on A and then my 2, I can kind of write it out here. All right, 1, and then 2's just 2, but 3, what I want to do is for 3, I put it in the columns now that what 1 plus 2 is what 3. 4 is 4. 5 is what 1 plus what 4. So I put a 5 here and a what 5 here. 6 is what 2 plus 4. So 6 and a what 6. 7 is 1 plus 2 plus what 4. Then I get to what 8. And then 9 is 1 plus 8. So I put a 9 here and a what and keep going. And eventually you get down where you get to 31, and then it's going to be 1 plus 2 plus 4 plus 8 plus what? 16. So this used to, what I did after I turned 32, and this would no longer work for me, I used to make an assignment back in the day, come back in and build me a table that my age could be found. And what you would have to do then is create a column what? F. And so you would have the 16, but now you'd have what? 32, and the bottom row would, so if the table's gonna get, bigger, have a lot more rows, another column, and then the last number is gonna be 63 across. So I am not 63, I'm not quite that. I have said once I'm older, if that table, the revised table won't work for me, then it's time to call it a career for sure. All right, any questions on that? Okay. All right. So you can see across there, which was table 13. So this table was also on page 173. See that table right to the left of there. So you're not gonna have anything this extreme on homework. But you are gonna have some problems where you actually have to convert. It'll take a number and it'll say, go from 24,243 base 6 and convert this to base 8. All right, you have no choice. You have to take this, convert it to base 10, and then from that base 10 form, put it to what, base 8. You have no choice. Remember I said hexadecimal had some practical application. So does base 8. So here would be a problem that I would put on, if you were back in the day and taking written tests. I would always have this problem on the test. Don't write this down. I'm making this up. Earlier now. And I would say convert to base 16. Yeah, right. That's, you're not kidding. So, well, we're gonna, why would I make it this obnoxious? Let me figure out how many place values we got. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 3, 4, 5, 6, 7, 8, 9, 30, 31, 32. That is 1 to the times 2 to the power of 32. If I just go 2 to the power of 32, on my calculator, that comes out $4,294,496. That's it, and that is just what one place value. Eventually, it's going to start putting the number in, it's going to start rounding it off and putting it in scientific notation because it's going to get so big. Not practical. So is there a shortcut? And the answer is yes, there's a shortcut. And that's why I would make it so many digits. Making it so that the only way you could do the problem is by the what? Shortcut. That is, when we say shortcut, what I really mean is I can convert directly from base 2 to base 16 without having to go through base what? 10. Now, why would that be? Why could I not? I said, this one you can't. You have to go through base 10. There's a relationship between base 2 and base and 16. 2 to the what? 4th is what? 16. Anywhere you have that base to a counting number power to equal that, there's going to be a direct conversion. That means there would also be one between base 2 and base 8. Theoretically, between base 3 and base 9. 3 squared is what? 9. But there is no counting number power I can raise 6 to and get what? 8. So that's why you have to go through base 10. All right, so you see this table here. I want to build it. I'm going to build it right here on the board. So I'm going to put base 16. Should be nothing. Now I have another problem here. All right, so I'm going to do is write down all the base 16 digits. 0, 1, 2, 3, 8, 9. All right, now we got to do what? A, B, C, D, E, and F. And then just kind of aside, we know that that is in base 10, 10, 11, 12, 13, 14, and 15. So remember, for what basically this tells me, if 2 to the 4th is 16, every base 16 digit can be represented with a 4-digit base 2 number. Or what we call binary. Before, now you don't have to do this. I'm gonna put lines in here just so I don't start mixing things up. All right. So remember that we're going to be in base 2. We're just to find any number, have to find a combination of powers of 2 that add up to be that number. So that would be for 4 digits, you have 2 to the 0 plus 2 to the first, 2 squared, 2 cubed. Which again, that's 1, that's 2, that's 4, that's 8. So 0 is easy. It's all zeros. Now, 1, again, you just want to pick off what you need. And what you need to put a 1 in for. What you don't need to put a 0 in for. So it's 0, 0, 0, 1. 2 would be 0, 0, 1, 0. Good. Okay. So 3 would be 0, 0, 1, 1. 1 plus 2. Got it? Okay, so making sure. So 4 would then be 0, 1, 0, 0. 5 would be 0, 1, 0, 4 plus 1. 6 would be 0, 1, 1, 0. 7 would be 0, 1, 1, 1. 8, 1, 0, 0, 0. 9 would be 1, 0, 0, 1. 10 would be, we need what, 8 and 2. So 1, 0, 1, 0. 11 then would be 1, 0, 1, 1. 12 would have to be 1, 1, 0, 0. 8 plus 4. 13, 1, 1, 0, 1. 14 would be 1, 1, 1, 0. And then finally 15, 1, 1, 1, and what? 1. Okay. Now, back in the day, in written test, you would have this problem, but preceding that, I would say construct the table, write the table. And, so you can set and what, do the calculations individually. But you can also do this by pattern. Look at 1's place and just go down the column. Every what? Go to 2's place, 2 the first, 2 zeros, 2 1s, 2 zeros, 2 1s, 2 zeros, 2 1s. 2 the squared, 4's place, 4 zeros, 4 1s, 4 zeros, 4 what? And then finally 2 to the third place, 8 zeros, followed by 8 1s. Now, so how do we use, could we use this to do this? So theoretically, you actually really don't need the table if you just do these calculations individually. But if you have the table, you can speed it up a little bit. Start over in 1's place. Now remember, we're wanting to what? Convert this to base 16. Go every what? 4 digits and put a partition in. Notice I exaggerated. Why did I make that really big? Not to confuse it with a what? 1. Now just go again, partitions every 4. And if there's something left over, you can put insignificant, you can put what, 0, 0, 0, what, 0. Not significant. Now, you either again, you just convert them individually in your head, or you go to the table And say, okay, this one is what? D. And this one would have to be what? A 5. This one would have to be a 5. This one would have to be a what? D. C, thank you. This one would have to be B. This one would be E. This one would be a 6. This one would be a B. And then that would be a what? A 1. Which one? Which,
E should be E.
this one?
E.
E should be D.
D.
You're right. Yep. Okay. So then all you have to do is what? Base 16. So again, what looked like a horrific problem really is actually what Lightning Bolt. And if you were going back the other direction, it would just be a matter of take that and then write what as a 4-digit binary number. What's that?
You do not replace D.
Yep, sure can. Now, here's the thing, and you can't see this on this table here. Drives me nuts. People would forget to log out. And so it's set. I wish it wasn't so, but it's like every 3 minutes or something. It shuts off if I don't do something with it. It's kind of a pain anyhow. So every base 8-digit 0 through 7 would be somewhat 3-digit what binary number. So if you have this table, you don't need a whole nother table. You got a table within a table. Count number 3. And do that. So the 0, 0, 0, 0, 1 is 0, 0, what? And it's right there. And then up to 7, which would be 1, 1, 1. So, yep. And you'll have some. Now it will say go from octal to hexadecimal. Octal is 8, hexadecimal is 16. Okay. Binary is 2. Okay. I think the only thing I haven't talked about today is actually not in the textbook. It's in the problem sets. So it's in the textbook, it's in the problem set. They won't actually discuss it. No. Ah. All right, one more time. All right, ASCII, ASCII, American Standard Code of Information Interchange. So this just deals with letters, doesn't deal with punctuation. Somewhere in my filing cabinet down in my office, I have actually the whole ASCII code for punctuations for everything. This just talks about letters. It says capital letters A through Z are assigned the numbers what 65 through what 90. And lowercase letters are A through Z are 97 through 122, so 26 letters. Now, so all this problem comes up to, this says find the binary code for letter K. I'm not going to do K. If A through Z are assigned numbers what 65 through 90, and I said find capital letter C, its base 10 number would be what 60 what 7. And then if I wanted to convert 67, again, this is where I do not
you can do the division, start dividing by 2 and getting remainders. It's gonna take a little bit longer to do it that way. But since you're going to base 2, I just think about place values. I've got this. If I continued on, 2 to the 4th, 16 to the 5th, and 32, and 2 to the 6th, 54. It's finding a combination of these that come up to be this number. So 67 would have to be 64. Wouldn't want 32, wouldn't want 16, wouldn't want 8, wouldn't want 4. We do want the what, 2 and the what, 1. So 64 plus 2 plus 1 is what? 67. Now, technically for ASCII, we don't usually what, put that on there. But ASCII is those problems are simply converting to base 2. The hardest part to me isn't this, writing conversion. It's finding what number that letter corresponds to. Like they got the letter K, that couldn't be, that's almost dead center. So you got to count. You got to start going A, B, C, D, and what corresponding to the numbers. Okay, you guys got any questions? All right. I think I have covered everything. So let me, your homework is going to be 4.4, finish it out. I originally said 1 through 20.